When a digital platform is designed to match users for physical, real-world interactions, it inherits a massive layer of physical vulnerability. The system has to govern exactly who is allowed to meet offline. In platforms like Project NEXUS, content moderation abandons basic profanity filters. It focuses entirely on enforcing physical safeguarding and strict legal compliance across user interactions. For the user, this compliance is hidden behind a frictionless interface. During onboarding, a clean React UI simply asks, "Do you work with vulnerable adults?" alongside a blank checkbox. Checking that single box triggers an immediate, aggressive backend reaction. It initiates a cascading series of database locks, overrides standard user permissions, and dispatches high-priority asynchronous queues. Trust in enterprise software is built through the combination of strict database concurrency, automated event interception, and fault-tolerant asynchronous queues. Project NEXUS operates as a multi-tenant platform. This means it has to simultaneously enforce vastly different legal jurisdictions and country-specific compliance rules within a single codebase. To manage this, the system relies on a broker concept. A broker is not a separate user role. It is a strict administrative capability, a set of monitoring tools overlaid directly onto existing tenant admins. The central architectural challenge is reliability. The system must translate a high-risk user selection into a platform-wide lockdown without introducing race conditions or dropping data. We can trace exactly how this works by following a single safeguarding data payload. We will track it from the React client through a restrictive API lock into the database state machine and out through asynchronous queues. Tracking this single data lifecycle reveals exactly how external legal requirements dictate rigid internal backend design. The journey begins at the React client, specifically on Step 5 of the onboarding wizard. This step is governed by strict GDPR constraints. No pre-ticked boxes are permitted, and the application requires explicit capture of the user's IP address and timestamp to form a valid consent payload. Once the user clicks Submit, the post-request payload hits the /v2/onboarding/complete API endpoint, routed to the Laravel controller. The system's immediate response is illustrated here. The controller executes a select for update row-level lock directly on the database. This prevents a concurrent double submission race condition. Without it, a user mashing submit could bypass strict automated limits on listing creation. By locking the row, the application intentionally bottlenecks the traffic, prioritizing strict data integrity over pure system throughput. Legal liability requires the system to process these specific state changes sequentially, regardless of traffic spikes or server latency. With the lock acquired, the payload moves from the API controller into the internal safeguarding trigger service. The system reads a JSON file mapping the user's selections directly to database triggers. Executing standard OR logic, if any single option contains a restriction trigger, the service merges all applicable rules to find the strictest possible denominator. This logic applies direct updates to the user messaging restrictions table and hard-codes strict service flags, like no home visits, directly onto the user record. Because querying these rules on every subsequent API call would cause massive database load, the system implements a performance optimization. It caches these new restrictions for exactly 5 minutes per user tenant. Through this process, a single front-end selection completely rewrites the user's operational state machine and strips away their default permissions. Moving forward in the timeline, we reach the moment the newly restricted user attempts to send a message. They are met by the Broker Message Visibility Service, which acts as a silent queue listener, continually monitoring the messaging endpoints. Because the requires broker approval trigger was cached earlier, the intersection logic activates. The messaging endpoint immediately ceases to be peer-to-peer. The payload is duplicated mid-flight and silently routed into the broker message copies table, setting up a mandatory administrative review. This exact queued event fires under several other specific conditions. It triggers for the first ever contact between two users, during new member monitoring windows, or whenever a message is associated with a high-risk listing. The architectural solution injects mandatory human-in-the-loop oversight directly into high-volume matching algorithms, all without interrupting the immediate experience of the users. Not all system alerts are treated equally. The architecture strictly separates standard system notifications from critical safeguarding alerts. This routing path shows the standard notification logic. Routine events utilize pusher WebSockets for real-time delivery over a private, user-specific channel. If the WebSocket connection fails, a secondary 60-second polling mechanism activates as a fallback layer. Safeguarding events carry strict legal liability. They cannot rely on standard delivery methods or respect user preference toggles. To handle this, the system introduces a dedicated routing primitive, the Notify Safeguarding Staff Queued Listener. This protocol forces notifications to all admins across email and in-app channels, completely ignoring user opt-outs. To combat network failures, it employs an architectural failsafe. The listener operates on a strict 3-retry exponential backoff schedule, firing at 10, 60, and 300-second intervals. Only upon the absolute final failure of this specific backoff sequence does the system execute a critical level log to the server. This redundant notification architecture ensures that critical safeguarding data persists through transient failures and forces administrative visibility, regardless of individual user settings. This full diagram captures the entire data journey of the safeguarding payload from start to finish. A single checkbox locks the database, rewrites user permissions, duplicates network traffic, and overrides system-wide preferences. This entire complex, multi-layered workflow happens completely invisibly to the end user in milliseconds. For back-end architects who are tasked with building complex compliance-driven software at scale, the ultimate implication is clear. True platform safety is not an abstract community guideline. It is an explicit architectural state achieved through rigorous system design.